of this session is to move from insights to action, focuses on solutions to address the energy challenges created by AI-driven data growth. We all know electricity demand is rising, grid complexity is increasing, and infrastructure timelines are tightening. The question is not whether AI will scale. It already is. The question is how we deploy data centers that enhances resiliency, flexibility, reliability, and performance. So let's dive into solution. So first, I have Jacqueline Cochran from the National Lab of the Rockies to give the opening remarks and set the context. Jacqueline.
Great. Thank you, everyone. So my name is Jacqueline Cochran. I'm an Associate Laboratory Director at the National Lab of the Rockies. You may remember us as National Renewable Energy Lab, and our name changed in December. We are still the same people, same buildings, amazing research. We're located in Colorado, which is that green dot. So all the rest of that is other Department of Energy laboratories, and as a whole, we work on the research that's long-term, has like grand challenges ahead, and there is nothing that speaks to a grand challenge more than AI and data centers. We work with over 80 countries around the world on advanced energy systems, including with India for over 20 years. At the National Lab of the Rockies, our science drives innovation. We work on energy systems integration. So for example, grid modernization. We work on transportation and fuels such as hydrogen, fuel cells, biofuels. We work on buildings and industry. So advanced building properties, advanced materials and manufacturing. And then also different generation sources like geothermal, hydro, solar. A great example of energy systems integration is our work on data centers. Data centers are complex interconnected systems. And this chart shows that range of issues that we're all talking about when we're looking at how do you expand data centers. So on the left, we have the chips, and some of the research we're doing there is on how can we create newer chip cooling solutions. And then on the rack side, how can we improve the power density to improve the power electronics to manage ever increasing power density sizes. At the facility level, we're trying to understand how can we better manage the load, both electrical and thermal. And on the campus, for campuses that have backup storage or behind the meter generation, what is the optimal sizing for that? And then, of course, as it's connected to the grid, the distribution grid, data centers now are even developing their own substations and distribution systems, the transmission and bulk generation to meet all this demand growth. This map shows is data center infrastructure in the United States. And what it shows is locations where it would be easier to build data centers based on existing infrastructure, such as the location of fiber, optic cables, and transmission lines and generation sources, which are illustrated in the map. The challenge here, as it is everywhere in the world, is that we need to get things built, and we need to get them built fast. But the people who are responsible for building things quickly are trying to manage many competing goals. They're not necessarily competing, but there are many goals, but they do compete with each other. For example, we need to make sure we have the fuels and materials and an infrastructure available. Our energy needs to be affordable. Utilities need to be profitable. The grid needs to be reliable. And people need to make decisions based on incomplete information and to be able to do so quickly. So one of the challenges that we have at our laboratory is how can we use our models and data to be able to help address all of those goals together and optimize across many different stakeholders and many interests in the development. This is an example of some of our modeling where we just peel apart data center, like just citing a data center is very, many different complex factors that go into it in terms of, especially what we were hearing this morning too, on the pricing, the affordability aspects, the water availability, the proximity to related infrastructure. And so at our national laboratory, we use our geospatial capabilities to really dip into each layer and be able to look across different, even local ordinances of, how close can you be to a school and things like that, that will help us look across, all right, how do we build out the natural gas pipeline to optimize around data centers or optimize around data centers plus new manufacturing? And then at our laboratory, the National Lab of the Rockies, we couple that modeling and data analysis with hardware, experimentation, testing, validation, so that as data centers and as people are bringing on new technologies, they want to be able to know that it works as expected. And so that's what we do at our laboratories. We do different, and my colleague Murali Bagu will be going into this in more detail, but looking at different controls, different load management, power electronics, and thermal management. And then finally, we're not just looking at data centers at our laboratory, but we're looking at AI across the whole research portfolio. So looking at for example, the top left, core AI methods, how can we use AI to better operate the grid? And on the right, how can we have more trustworthy, scalable infrastructure? So for example, can we use AI to do more red teaming, adversarial testing for grid security? In the bottom left, energy applications. How can we use AI, for example, to do more autonomous energy management or critical materials processing? And then finally, on the mission impact on the bottom right, what can we use to make our research go faster and more efficient? We are a taxpayer public institution in the United States, and we want to use AI to accelerate our research findings and to do so at less cost. And so with that, I'm going to turn it to Murali. I think you're next, right? To my colleague Murali Bagu. He's the lab program manager of grid integration at the National Lab of the Rockies.
Thank you, Jacqueline. Thank you for setting the stage. Thanks, everyone, for taking time to attend this particular session. I'll just dive a little bit deep into the capabilities at the National Lab of the Rockies. My name is Murali Bagu. I'm a laboratory program manager for grid integration, works very closely with the Department of Energy's Office of Electricity and other grid offices to execute on this particular mission. I'll actually dive directly into research capabilities because I know Jacqueline did a great job of introducing different issues that we see with data centers. So just to begin the thought process here, as you can see, right, I mean, there is a lot of complex systems involved in data centers, all the way from chips, softwares, racks, facilities, all the way up to the grid side, which is distribution, transmission, and generation. I think we do work on all these gamuts. We call this the chip-to-grid approach for what we're doing, and actually do a co-optimization of the integrated energy system all across the gamut. I'll probably touch on more on the grid side, given the interest of the panel here. But as I said, we do have a holistic approach across all the different areas that we're talking. Let me talk about our data center that we have at the National Lab of the Rockies, which we call the High Performance Computing or Data Center, which is a living laboratory. As you can see, we have our own cooling and data center in the middle of the picture right there, and other things. But the main aspect is, this particular data center really spans to like a 10,000 square feet facility with up to 10 megawatt of computing power. So pretty big to learn what really happens inside the data center. We also do large-scale modeling, simulation, and AI-driven research in this one, so we can actually put in diverse loads on the data centers to understand what it's going to do. We have a very good, what I call, innovative cooling method for this particular data center. We use component-level liquid cooling with water, and then we actually use that water once it gets heated to heat the building and other things. So we squeeze heat out of the water that is coming out of this particular data center and circulate it inside the building to really do heating the building and other things. This particular data center really enables us to collaborate with our partners, evaluate advanced technologies, and also optimize operations for data centers and validate new cooling and power methods that are used across real-world solutions out there. So in a way, we are the guinea pig to look at what this looks like when it scales up in all other data centers out there in the world. I'll get into a different facility, which the data center is part of, which we call the energy system integration facility. This actually have the other side of the equation. The grid side of the equation is what we have here. We can really create our own grid to connect to this particular data center or to any grid integrated holistic research that we are looking at. We can actually create virtual utility operation rooms in there, any smart grid interoperability and cybersecurity level testing in there. And we have assets of all the way up to megawatt level to do hardware in the loop experiments to really test how different data centers work and, when interacting with the real grid. We also have what we call the distribution management side of things to look at how the management of these things really happens on real time when it comes to load management and other things. The pictures there actually shows a setup of both simulation and hardware on one of the data center projects which I'll talk in one of my examples. I'll actually get to a different facility, which is also at National Laboratory of the Rockies, which we call the Advanced Research and Integrated Systems Flatiron's campus. Here we actually have all the way up to 10 megawatt levels. So again, the size really matters when it comes to data centers. We need to make sure we have big size to test different applications, different control methods. Three examples that I'm showcasing here is one we call the power electronic grid interface. Which is a bidirectional power electronics device that can be connected to different UPS and other different applications of data centers to test how they really work on real-time basis. The other one, which I want to mention, is advanced power electronic test bed, or APT to be precise. Which actually looks at MVDC or medium voltage architectures for data centers, and even going all the way up to HVDC, depending upon the size of the data center we're looking at. Not listed here is actually what I call the storage pads. I know there was actually discussion on storage in our earlier session, where we look at different storage applications to see how they help mitigate issues that might arise on the data centers. Just to talk through the whole picture here, these are some of the tools that we use to support data center deployment all the way from planning to operations. Jacqueline mentioned some of the graphics there, which probably use some of these tools like REITs, Sienna, Rev, and Reopt, and others, which we use to both optimize as well as plan for data center applications. Let me jump into some of the example projects real quick in the interest of time. The first one is, data center as a flexible load. I know this was talked in the earlier panel where we looked at, can we make it flexible enough so that grid and data centers can work in harmony is what the idea here is. This is a work we are doing with the Virus, a data center manufacturer, or I would say aggregator than manufacturer or integrator, where we're looking at data center supporting the active grid stability aspects of it. Can we really manage the load in such a way that where we can support the active grid stability? We are modeling a 70 megawatt data center in Ares platform that I mentioned, really completely doing the power flow solution and combining with the battery system so that we can show the flexibility of the system in this particular case. The second one is on energy. This is actually looking at different component of the data center. In this case, we are looking at how UPSs that connect to data centers. If you really look at data centers, right, we can't afford losing power even for seconds on data centers. So each of them have UPSs which take care of issues from seconds to minutes, and then we have backup generation which take it from minutes to hours to days. That's what in most cases. So the UPS is a very critical component of the data center. So in this case, we are looking at testing UPS for rapid load changes to see how grid disturbances. So if there are low voltage issues or harmonic issues on the grid, how that impacts data centers. And we're actually seeing UPS actually plays a very big role in doing those kind of things. The next one is with electric power engineers. I think one beautiful thing of having an HPC in-house is to really, we can monitor that HPC in all ways possible. So in this particular project is actually capturing how can we come up with different load types, for utilities. We are working with electric power engineers on this particular one, where we are modeling different utility interconnection processes and also coming up with different load shapes for data centers on this particular one. The last one that I will showcase is the hybrid generation for pulsating loads. This one, I think we used all the assets in our ARIS to really recreate what a data center load looks like. The data center loads really pulses a lot depending upon the batch processing that it does. So we're trying to see if we can use our regular base load resources along with energy storage and other dynamic power electronic resources to really segregate the load in two parts, where some of it can be taken by base load and some of it can be taken by variable energy storage, is what we are trying to demonstrate in this. I have a nice video for this. I'll probably get into the video and then I'll conclude my talk here. Let's see.
In less than a second, a data center's power demand can drop or grow fivefold, sometimes unpredictably. It's like flicking a giant light switch up and down on 10,000 homes. How can the electric grid or a company that owns a data center power such a large, rapidly changing load? Answering that question requires a real power system that can simulate these exact scenarios at high fidelity. And to do it, the U.S. Department of Energy has the ARIES platform. In a project sponsored by the Office of Electricity, power system experts showed that using a mix of energy resources can tackle the challenge of powering data centers. See how they did it. First, they modeled a power grid. They built a scaled-down data center and its power sources, identical to what exists in cities across the country. Next, they used a generator that can replicate gas, nuclear, or geothermal power, along with real batteries and fuel cells for fast responses to large load swings, and, if needed, backup power. Then, to simulate dynamic power demand, they leveraged energy data from a leading AI data services company. Finally, they initialized the grid scenarios and pressed go. The first thing they noticed was wear on the generator. The data center's cyclic demand put torsional strain on the shaft, which is not built for rapid start and stop power. If this were to continue unassisted, the generator would soon wear down. But when it is combined with other technologies like batteries and fuel cells, these more responsive resources supplied the pulsating loads, so the generator could spin smoothly, providing steady baseload power. The researchers then went a step further and simulated a generator failure. When this happened, the battery and fuel cell temporarily provided reserve power to keep the system running. The combination of baseload generation, integrated with other technologies, could be the key to low-cost, high-reliability power for data centers, AI, and more. And that's just one of the many experiments made possible with ARIES. This is your platform. Find out how your company can advance power solutions with ARIES. In less than a second.
Thank you. I would like to introduce my next speaker here, Abhijit Abhyankar, who is the chair professor of electrical engineering at IIT Delhi, to talk about research and innovation to tackle energy challenges for data centers. Thank you.
Good morning, and thank you, NREL, rather NLR, for having me. Sorry about that. Uh, and what a lovely presentation we had from Dr. Baggu, taking a deep dive into the technological aspects of data center. So let me bring some academic perspective into this whole discussion. What I'm going to discuss very briefly is the nexus between the energy and AI, and what are the research and collaboration opportunities for researchers, research institutes, general researchers, academia, lab people, and industry. Now, all of you have been hearing about this, the data centers, the importance of the same. It's basically, it forms the core of any digital infrastructure for cloud, AI, fintech, IoT, e-governance kind of activities. And you know that generally speaking, there are two types of uh, data centers, hyperscalers and co-located. And they are supposed to operate 24 by 7 with high redundancy and reliability requirements. Why energy matters when we talk about data centers? This is because, simply speaking, the data centers, especially the AI data centers, they are power guzzlers. And this accounts for major share in OPEX. So if you compare this with any manufacturing unit or a factory, the input to data center is nothing but only and only energy, right? And the output can be some meaningful information, which is based on certain level of computation. So there's great deal of energy involved. There's a significant carbon footprint involved globally. There's a lot of talk happening these days about the kind of decarbonization or the hurdles in decarbonization that the AI data centers would put in. And of course, there is some element of truth in that. Let's say if we talk about the requirements of any data center, one of the requirements apart from the power and energy is the water requirement, fresh requirement, because the modern data centers, they are going to be liquid cooled. So just to give you an example, let's say if you give 50 prompts for to get some response from your chat GPT or something, it results in consumption of about half a liter of water, fresh water. So a typical 100 megawatt data center consumes about 20 lakh liters of fresh water per day. Apart from that, the equipment that is used in data centers, the IT infrastructure, it involves gold, silver, and many rare earths. And the mining of the same also has got carbon footprint involved. So these are certain concerns that people are talking about. There's energy security and grid impact concerns. That means the data centers, AI data centers, they are going to be huge power demanding clusters, perhaps embedded within the distribution systems, or if the data center is a real hyperscale data center, then there is a chance that it may get connected to the transmission systems as well. So how do you plan for the same, so long as delivery of energy, electrical energy is concerned? So that is something which is very important from the point of view of planning per se. Then there are environmental, social, governance, and sustainability compliance pressures, which add burden, energy burden to the data centers. Okay, so AI's impact on energy demand. As I said, the AI requires high density GPUs. Now, gone are the days. The AI data centers, they don't work on CPUs. No chance. You need GPUs, but then the GPUs also, if you talk in terms of the rack requirement, the power requirement for the rack, it is minimum 100 plus kilowatt per rack. Okay. Add to that, you have AI accelerators like neural processing units, tensor processing units, which again are they demand a lot of power. The LLMs, they also significantly increase the compute demand. There is huge deal of training required, thousands of, hundreds of billions of parameters which train the large language models, and that is also significant. There is a significant demand of energy. Higher cooling and power infrastructure requirements. So just to give you some number, about 40% of the total, typically 40% of the total requirement of energy for data centers is consumed in cooling, right? So you can imagine the kind of requirement. And highest reliability requirements. The data center should have 99.99999 percent reliability. What it means is that data center should be 24 by 7. So if you want to achieve that kind of reliability, then you need backup, backup to backup, backup to backup, right? For example, now in India, we are talking about edge computing data centers, right? So this will result in having tier 2 and tier 3 cities having, small data centers located around them. And then if you want them to be reliable, have a reliable, power supply, then you have to add DGs apart from the battery storages. Now the DGs, with them you have to make provision for large storage of fuel, that is diesel. So they talk about decarbonization, energy requirement, and all this. It goes in circle and circle. We have to have solutions to this. Globally, data centers, they consume as of today about 1 to 1.5 of total electricity requirement. That and hyperscale facilities, they are increasing day by day. And it is projected, of course, there are a lot of numbers floating around. So one estimation is that electricity demand will be doubled by 2030. If you look at, now let's come to some research discussion. What are the opportunities? So let us start, or let us have this figure in front of you. And this is a typical energy flow for any data center. When I say typical, it's just the representative picture. You can see that the power electronic side, it consumes about, the losses, they are about 7 to 10% in a data center. The IT load, it consumes about 20% of the total requirement of data center. And the major focus is on cooling. About 40%, as I said, it goes and sits or as a requirement of a cooling load. And then other you have about 10% or so. So if you focus on this slide, you can easily understand where to focus, what are low-hanging fruit, so long as to solve energy and AI nexus, or to make AI more energy efficient. So this slide shows 4 quadrants, okay, which talk about what could be the research trends pertaining to energy in AI. Now, I'm not discussing here the chip related research and power electronic related research. They are walking their own path, right, and very neatly, nicely, in a committed fashion. So I'm not going to talk about that. But if you focus on the 20% of the IT requirement of energy and 40% for the cooling requirement, you can see that if you focus on this, these are the 4 quadrants which come in front of you. The quadrant number 1, 2, 3, they talk about improving the energy efficiency of data center. So if you talk about energy efficiency, nowadays there is a research that is going on thermal aware server placement. So how do you optimize the workload so that you optimize on the overall thermal loading of the data center? Similarly, energy is another attribute. So along with energy, how do you optimize your workload and allocate the work to different servers so that you optimize on energy? That's one way of carrying out research, quality research. Second is server consolidation. So as of today, the idle energy consumption of a data center typically can be of the order of 30, somewhere between 30 to 50%. So that means the data center is comatose, doing nothing, sleeping, but still it continues to consume 30 to 50% of the energy. So that's a challenge. So how do you overcome this problem, right? Or how do you improve the situation? So you can do optimal server consolidation. So there are algorithms people are working on dispatching appropriate set of commands or the workload to optimal set of servers at the operational stage as well as planning stage. So how do you do that? That's another level of research. Cooling, there is great deal of work that is currently going on. So you have 2-phase and single-phase immersion cooling systems. Single phase is where you have data centers. The IT infrastructure is embedded into a dielectric liquid material. And in 2-phase system, you have evaporation and condensation of some liquid that is happening. You have direct-to-chip cooling where the racks are connected with the cold plates, and the liquid fuel is liquid coolant is made to flow through these cold plates. So people are working on this. And the 4th quadrant, if you see, this is very important. So the first 3 quadrants that I spoke about, they talk about energy for AI. Okay, the 4th quadrant research group is AI for energy. How can you use AI to improve your overall energy perspective, overall energy situation. Now, this list in itself is 1 hour lecture in IIT Delhi, but I've condensed it to just 3 points, which I feel are very important for discussion over here. How do you use AI for energy? Basically, in my personal opinion, the great deal of advantage if you of AI is in distribution systems. If you make use of the same, for example, forecasting, scheduling in the wake of large-scale renewable integration, uncertain variable, the forecasting plays a big role. And now the epo change has come where you have to use AI for forecasting, extracting maximum juice out of DRs. So how do you make DRs available for system operation? How do you extract juice and create various commodities out of the same DER for overall system efficiency? That's another line of research. Load modeling and DR potential. So how do you do the NILM, non-intrusive load modeling, so that the distribution system gets to know what kind of load it has, right? And then take decisions, like it can come out with what is the DR potential in certain clusters and come out with certain regulations and policy. Well, this list can be very big. Before I move on to the next slide, let me just tell you that there are two hidden messages in this particular slide. Number one, you can see that the research areas, they are zoned out in various, they occupy the entire spectrum of knowledge. So when you want to carry out research, you can't work in silos henceforth. If you want to work in a AI and energy nexus, that is, you want people working on energy, you want people working on power, you want people working on material science, you want people working on thermal energy, and policy regulation. So there's a great deal of opportunity where entities, institutes, people working in these areas, they come together and work towards the common goal. That's number one. Number two message over here is that there is certain kind of circularity involved in this, that is AI for energy and energy for AI. So what it means is that if you take good care of the AI, so long as energy requirements are concerned, AI is likely to take good care of the energy part as well, right? So before I stop, this is my last slide. Let me just quickly give you the projection so long as Indian condition is concerned. So on the left-hand side, you have a map which shows the data centers. So the black dots is the existing concentration of the data centers as of today: Delhi, Mumbai, Hyderabad, Bangalore, Chennai. The blue ones are emerging hubs, right? So you can see in Ahmedabad, Pune, Vizag, Kolkata, these are emerging hubs. And there are edge data centers. So you can see a few tier 2 and 3 cities as yellow dots where there is a chance of data centers emerging. The projected data center load by 2030 is 5 to 8 megawatts in India. This is India specific. Of course, there are multiple numbers, but 5 to 8 is the common range. That is the common projection. And by that time, we expect that projected generator installed capacity would be 750 plus gigawatts, out of which around 500 will be non-fossil. So the decarbonization angle, we really have to see how much importance should we give it to that particular aspect. Edge computing, I have talked about. Data localization is Government of India policy. And India AI mission is supporting the PG students in a great way. So this India AI mission is supporting about, I guess, 500 PhD students, 5,000 MTech master students, 8,000 UG students in next 5 years. And one important thing that usually gets unnoticed is that the national education policy, which was floated in 2020, has got mention of AI, and it states that the students of grade 9 and onwards, they should be given flavor of AI henceforth. And Bharat Gen is the new LLM initiative that consortium of IITs has taken up, and ANRF has DST has funded it. And I think I should stop at that. Thank you so much.
Thank you, Dr. Abhyankar. So now let's go to the next presentation by Dr. Ghosh.
Good morning. First of all, let me thank the National Laboratory of the Rockies. NREL has become NLER, but friends are friends by any other name. Thanks for organizing this very important session, and it was really illuminating to hear about what you're doing in Colorado. And Professor Winkler, a lot of the issues you've highlighted are extremely pertinent, especially for India, where our energy and our water demands are growing not just because of AI, but AI is the latest sector that's adding to that demand. So what I'm going to do today in my presentation is present about this report that we just brought out. There's a CW and systemic report on scaling India's data center ecosystem, drawing very much on the broad themes that you've heard about already to understand to what extent are we ready and what more do we need to do. I represent the Council on Energy, Environment and Water. We're one of the world's leading climate think tanks. As you can see from the map, we worked with 20 state governments in India, several ministries of the central government. This year, I'm also chairing the AI and Climate Global Expert Group for this AI Impact Summit. So particularly privileged to have drawn on the wisdom of many experts from across the world. As we've already heard, AI runs on water, energy, and planning. It doesn't run just on code. The adoption of AI is, of course, accelerating at an unprecedented scale. Globally, it seems 1 in 6 people are using generative AI for some kind of activity. More than 90% of organizations globally and in India have adopted AI in at least one business function. Contrast this with the speed at which the internet was used. The pace of diffusion of the technology is much faster when we come down to institutional or organizational levels. AI workloads, of course, could then represent about 50% of all data center capacity by 2030. And India's AI market, of course, is growing. This means that there is a surge in the data center capacity. The global number could reach 200 gigawatts. Professor Abhyankar gave the range of 5 to 8. We have a slightly more conservative range, but broadly in that same area of 4.5 to 6.5 gigawatts by 2030. That would mean it will intensify the water and energy demand. In India, data centers account for about 0.5% of India's current electricity consumption and about 150 billion liters of water. This demand is expected to grow twice by 2030. Globally, about 1.5% of global electricity is being used. This is equivalent to, say, the entire electricity consumption of Japan. Global data center industry consumes about 560 billion liters, enough to give water to 8 million residents. So the question here, therefore, is how do we ensure that the AI growth runs in parallel and intentionally in sync with optimized use of resources? So there are a number of factors, therefore, that we'll have to keep in mind when we think about where to site the data centers. Firstly, do we have uninterrupted power with reliable backup, especially if we use cleaner power sources? Secondly, do we have adequate water for cooling and operations and efficient draining for the water management? Thirdly, do we have the right connectivity, the proximity to fiber networks and subsea landing stations for high-speed connectivity? Utilities, do we have access to transport, to supportive public and policy regulatory frameworks, clear sites from interference with other kind of signals? Are those locations resilient against climate shocks and extreme climate events, whether it's a flooding event, a storm surge, etc.? And then are we making it future ready, not just leveraging the present? Is there space for growth in a modular way as we look towards the growth of data centers? And as Professor Abhyankar already mentioned, and our report also identifies, you already have Delhi, Mumbai, Chennai, Bangalore, Kolkata as already the emerging hubs. Notice that many of these are along the coasts. So that might be a strength, but we also have to leverage or protect against potential weaknesses. So optimizing for these additional resources means that there is going to be trade-offs. If you want to have, say, air-cooled systems, you'll reduce water consumption, but you'll increase energy consumption. If you have an energy restriction, but you have water availability, you can switch to water-cooled systems with high water consumption, but lesser carbon footprint. So ultimately, the choice of the cooling technology will depend on location, will depend on choke points, will depend on operational efficiency. We also see, and some of this was also identified in Mr. Bagu's presentation, there are advanced cooling technologies, direct-to-chip cooling, dielectric plate cooling, etc. But like with any advanced technology, we face challenges of high upfront costs, supply chain issues, limited vendors, etc. That doesn't mean these are insurmountable. We've done this with clean energy, we've done this with batteries, etc. How do we design public policy that enables for the adoption of the most efficient technologies, incentivizes them through the lifetime of the operation, rather than put the burden of the upfront costs right up front? Now, one of the things we notice, therefore, is that, like with many things, there is competitive federalism even in India when it comes to data centers. We don't have a national policy framework that is binding for data center development, but as we heard from the recent budget, there is the data center development has been granted infrastructure status, and there's a long-term tax holiday over the next 2 decades. But in the absence of a central framework, several states have taken the lead. From that map, you see about 15 states in India already have notified dedicated data center policies as part of their industrial policies to attract investment. However, we find that only 5 of those 15 states in their policies have sustainability-related provisions. So we think we need to inject this with a degree of intentionality to fill 3 systemic gaps. Understand the water governance deficit, look at the performance standards, whether it's power use effectiveness or water use effectiveness, or even the carbon effectiveness that was mentioned earlier. And then, is there sufficient resilience against climate risks? If we can inject these frameworks, then we estimate that the investment attractiveness will actually increase, because there'll be more confidence in the kind of infrastructure that is being built out. So as I close, how could then India position itself as a sustainable hub for AI and data center development? First, and here's the formula, first measure what you manage. There should be mandatory disclosure of environmental footprints for all large data centers. We should perhaps aim for a national AI energy star rating, maybe even an AI water star rating, and provide the regulatory clarity early on so that industry is ready and knows what it's heading into. Second, site with foresight. Evaluate the water, land, and energy requirements in advance. Do your resource adequacy mapping so that your data-driven decision for siting can be made into a tool that helps industry. And then accordingly prioritize data center parks and co-locate with renewable energy sources or where water is more plentiful. Third, innovation and optimization. Let's adopt a right-sized approach rather than just compete for compute power. So how do we encourage public-private collaboration to accelerate more R&D in advanced cooling systems, in battery energy storage deployment, to have better demand response participation in managing the grid more dynamically? I'm sure Reggie will have things to say about that. And finally, keep humans in the loop. We need to leverage AI to support human-based decision-making, not replace it. We have to prohibit automated enforcement actions without human review. Ensure that there is due process and accountability embedded in our institutional architecture as much as it is in our data architecture. If we get this formula right, we can be ready for the future and make sure that the AI revolution serves the public purpose for which we've all convened today. Thank you very much. Look forward to the discussions.
Yep. I would like to call Raji to give the closing remarks.
Thank you, NLR, for inviting India Smart Grid Forum for this very important topic. 3 minutes given, 3 topics. Number one, about the grid challenge. We heard in the presentation, Professor Avengar said 8 gigawatt of data center load, which Arunava has brought it down to 5. But last week, I heard one very senior official from the Ministry of Power said that they have visibility to demand for 16 gigawatt. By 2030. So now, as most of you know, an AI data center load can go up and down up to 80% in few seconds. So even if we take 10 gigawatt load by 2030, that 80% up and down, that is coming down to 200 megawatt and 1000 megawatt in few seconds, depending on the computational load in any continent or on the orbit, is something which the grid operators are here, Samir sir and Narasimhan sir are here. How are we treating this? And all this, over a century, we planned the grid with N-1 reliability standard. For a data center, they are talking about N+1 and N+2. It's an entirely different paradigm shift. Coming to the second point, a very recent report I seen that a lot of protests, massive protest in US, particularly in the East Coast, where PJM has 30 gigawatt of connection requests for data centers by 2028. And if all that connections are given, average household electricity bill can go up by $70 per month. And in Texas, there are 240 gigawatt of connection requests pending till 2030. So where is it going to take? How regulators and policymakers are going to address this issue? Third point I'd like to highlight is, last 2 years, our favorite topic in every such forum was talking about AI for energy and energy for AI. And we debated that in our one event in Bombay in November also for 2 hours, all distribution utility meet. And a week later, Star One Cloud has taken an H100 GPU to the orbit. And I'm told that it is working perfectly and doing high performance computing load in last 2 months. And that has encouraged Elon to announce 1 million satellites where data centers will be hosted on the orbit in the coming years. So if trillions of dollars investment on the grid, which we are going to make on ground, what will happen to that if all the data centers are going to be on the orbit? These are points to ponder. I stop here. It was a great presentation. Many points where there are no solution. This 10,000 square feet, 30,000 square feet data center to square mile data center is something which happened in 3 years. It didn't happen over a decade or a century. So this is something new. Unknowns are dealing with we. And everybody has to work together. And our NEP, National Electricity Policy 2026, is little oblivious of this data center challenge. We have given some comments. I think maybe grid controller and other people will give more comments on that. Thank you.
Thank you all the speakers, and thank you all.